হ্যালো, 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 হ্যালো। না, শোনা যাচ্ছে না। হুম, তাহলে এক কাজ করুন।
Welcome again. So now we can start our session. So in this session there will be three talks, and the first talk is by Suman Majumdar, and he will be talking about proving the IgM physics and source characteristic during cosmic dawn using redshifted 21 centimeter bispectrum. Over to you, Suman.
Uh, I would like to first thank the organizer for giving me this opportunity to speak here and present this particular work. So this particular work is, or this presentation rather, is focused on these two archive entries. The second one has been published in JCAP, and the first one we are still fighting with the reviewer. So let me start. And before I start, I belong to this Department of Astronomy, Astrophysics, and Space Engineering. It's a rather new venture, I would say, kind of a new, let's say, startup company. So there are lots of ups and downs, and it's exciting. It's not smooth to be there. Okay. So we are recruiting PhD students. I know most of you are already PhD students, so I don't want to poach you any further, but you may know somebody who is still having some illusion about astronomy, astrophysics, space science, cosmology, climate change, remote sensing, etc. So please convey the message to them. By the end of this week, the application deadline ends. So if they are eligible, they have a gate or net qualification, ask them to apply. Okay.
So we have, other than the PhD program, we have 3 master's programs as well. One of them started back in 2018, which is MSc in Astronomy, and there are 2 new master's programs, MTech in Space Science and Engineering and MS Research in Space Science and Engineering, which started last year. So if somebody is interested in joining these master's programs, please let them aware that they do exist. It's a rather unique department in IIT system because, and one of the first in IIT system as well. It's a truly interdisciplinary department. We have, as I mentioned, we have researchers in, let's say, from various domains, starting from astrophysics, astronomy, cosmology, space sciences, remote sensing, climate change as well. So the work that I'm going to present here was mostly done by Mohammad Kamran, who was a PhD student in our department and recently moved to Uppsala University in Sweden as a postdoc. So I am pretty sure the previous speakers have already convinced you about the utility of 21 centimeter signal to probe the early universe, specifically the cosmic dawn and epoch of reionization. I would specifically focus on the cosmic dawn era, and I would specifically focus on 2 physical processes in the intergalactic medium. One of them is Lyman alpha coupling, the other one is X-ray heating. I would not talk about collisional coupling as such. So the aim or motivation here is to see how these 2 processes actually impact the IgM, or rather the spin temperature of 21 centimeter signal, and how does that manifests in terms of the fluctuations in brightness temperature of the 21 centimeter signal, and how you can actually quantify through a new statistic and then look for specific signatures of these processes in the 21 centimeter signal fluctuation. And I would rather start with the point that bispectrum actually provides you with a better handle to identify which one among these 2 processes are dominating and when. And why so, we will see eventually. So the astrophysics part that comes and or dominates the 21 centimeter signal fluctuation comes from specifically these 2 terms. One is neutral fraction, the other one is spin temperature. So the IgM processes affect the neutral fraction through ionization of the intergalactic medium or hydrogen, and the spin temperature essentially gets affected by the various astrophysical processes as well. So they dominate the 21 centimeter signal fluctuations, and there are usual ways of quantifying those 21 centimeter signal fluctuations. One conventional way is using power spectrum. Now, you can constrain or let's say quantify the signal just using power spectrum as long as it's a purely Gaussian random field. Now, the moment the signal becomes non-Gaussian, power spectrum does not remain the optimal statistic to quantify it. So, for that you have to go for higher order statistic, and one such higher order statistic is bispectrum. Now, the non-Gaussianity that we are talking about here is the non-Gaussianity in the 21 centimeter signal fluctuation, which is dependent both on spatial fluctuations as well as temporal fluctuations. So, the fluctuation changes with time, specifically if I look at the cosmic dawn. So, as I mentioned, these fluctuations are dominated by astrophysical processes that take place in the intergalactic medium, driven by the properties of the sources that drives the change in spin temperature as well as the ionization fraction in the intergalactic medium. So, this non-Gaussianity is intrinsic. You may think, okay, that might be true simply because of the fact the sources are distributed in non-random fashions, because we know the sources of ionizations, they are localized in certain regions where you have large masses of dark matter clustered. But that's not only the case, because if you just look at the source distribution, yes, that is non-Gaussian, but it does not evolve that much, that fast with time compared to the actual 21 centimeter signal fluctuation if you look at. So, there the time evolution of the 21 centimeter signal fluctuation is driven by the IGM physics. That is again in turn driven by the properties of the sources or the photons that are being emitted by the sources with time, and it progresses with time as well. So, it's a rather complicated non-Gaussianity which changes with location in sky as well as time or frequency. So, as I said, one way to quantify it, and this is just one way, there can be various other ways of quantifying this fluctuation. One way of quantifying it is by using the 3-point correlation function equivalent in Fourier domain, which is bispectrum, where you essentially construct a closed triangle of wave vectors or wave numbers k1, k2, k3, and essentially multiply the Fourier transform of the brightness temperature fluctuation in these 3 k vectors, as long as they form a closed triangle. If they do not form a closed triangle, then the ensemble average of this product will not be non-zero. Okay, sorry. Yeah. So, why bispectrum is going to give you this additional handle through which you would be able to distinguish between the different dominating physical processes in the IGM. The simple reason being that bispectrum can be both positive as well as negative compared to the power spectrum, which is nothing but a variance in k space or Fourier space as a function of k or wave number. So, because power spectrum is kind of a product and then ensemble average of delta 21 being the Fourier transform of the 21 centimeter brightness temperature fluctuation, then by definition it will always be positive. However, bispectrum, because it's a product of 3 deltas, that actually makes it, that actually creates a probability that it can be positive as well as negative. And we will use that sign fluctuation in bispectrum as a tracer of what physical process is dominating when in cosmic time. So, that's the motivation. With that motivation, we started this particular project, and we particularly focused on one type of K triangle. So, the speakers after me will discuss about various kinds of triangles that you can construct in Fourier space and through which you can actually quantify this non-Gaussianity in the signal in a more holistic fashion. However, I am being conservative and I will focus only on one type of triangle, that's called squeezed limit triangle, where 2 k vectors are very close lying and the third vector almost non-existent, it's almost close to 0, but not 0 for practical purposes. So, and we will focus only on small k modes. So, that will correspond to very large length scale in the real space. So, what we are looking at is essentially large scale non-Gaussianity. We are looking at quantifying the large scale non-Gaussianity through this squeezed limit bispectrum. Okay, so and we chose this squeezed limit bispectrum simply because of the fact it has the maximum amplitude, and we figured out that it will give you the maximum SNR as well if you consider roughly 1000 hours of SK observation, and these are rather analytical estimates, I must say. So the detection probability would be higher if you target this particular configuration of K triangle. And our hope is that through observing the bispectrum at squeezed limit small k triangles, we will be able to probe the IGM physics at significantly large length scales. So we simulated our 21 centimeter fluctuations using a 1D radiative transfer simulation, which was done by Raghunath Ghada, who is one of the SOC of this conference. We considered 4 different scenarios of the simulation. In the first 3 scenarios are rather basic, where we purposefully chosen that one of the physical processes is dominating and the other processes are subdominant, rather, just to look at its individual unique signature on the bispectrum. The fourth model, which is model C, where all processes are kind of taken care of in a self-consistent manner, there we would like to see what happens when all the processes are going on simultaneously and one process dominates over the other, whether we can still recover the similar kind of signatures that we have seen is associated with that specific process in the previous 3 models, which are rather simplistic. Okay, so that was the motivation of choosing these 4 models. So the model A naught has Lyman alpha coupling. However, it does not have any X-ray heating, and ionization. Model A has Lyman alpha coupling and ionization at later stage of cosmic dawn. And by the way, I should mention here, when we are considering ionization, we are not going into EOR. We basically stop our simulation somewhere around 10% ionized IGM only. So it's very early stage of EOR or late stage of cosmic dawn. That's up to where we have simulated. So in model B, we have a Lyman alpha saturated background to start with, and on top of that, we self-consistently simulate X-ray heating as well as ionization. And model C, where all 3 processes are running simultaneously and gradually one takes over the other. So this is our estimator for bispectrum. So let us start with model A naught, where Lyman alpha coupling is the sole dominant process. And what we find out is that bispectra, so please note that on the left hand side, this is the early stage of the universe, and this is the late stage of the universe. So the redshift increases from right to left, and the cosmic dawn basically progresses from left to right. So similarly, in this plot, the squeezed limit bispectra is shown here. It increases monotonically in amplitude or magnitude, whereas keeping its sign constant, that is negative, okay, during the entire CD period. Then at the late stage of CD, it kind of saturates, but not completely, but the basically progress of growth of bispectrum kind of is slowed down. Then in model A, where Lyman alpha coupling and photoionization both have been considered, we see that this model, that is the red dashed curve, kind of follows the black solid line up to redshift 13 or so in the same fashion. However, after that, the dashed curve changes its sign. Why does that happen? That happens simply because of the fact that ionization takes over in terms of determining the brightness temperature fluctuations compared to the Lyman alpha background, Lyman alpha coupling. So Lyman alpha coupling has more or less saturated by redshift 13 or so. Then ionization of the intergalactic medium drives the fluctuations of 21 centimeter brightness temperature. In model B, we have heating. So in the previous 2 models, we didn't have heating. Now we do. But the background or the IGM is already Lyman alpha coupled fully. So that means we start with a very high bispectrum, just as the black curve, more or less at the same magnitude or same amplitude. But then, because heating gradually takes over Lyman alpha coupling's dominance, we see a sign change, and then after a while, the ionization kind of takes over, or the heated regions the heated regions which were individually located and separated from each other, they start to basically connect with each other. So it becomes a large interconnected heated region at this time. So though this slice does not show the interconnection, actually it is starting to get interconnected because you are getting a cut of a 3D field, a 2D cut of a 3D field. That's why it is not necessarily obvious from this particular picture. So then in the late stage, we see the similar kind of evolution as when the X-ray heating is dominant, but on top of that, the ionization is also basically taking over X-ray heating. So the amplitude of fluctuation gradually decreases and it approaches the zero. So you see two sign changes. So now let us move to our most realistic scenario, which is the model C, where it is bispectrum is shown by that green dashed curve. So as you can see, at early on, though the amplitude is slightly different, it more or less follows the trend that we have expected from model A and A naught, where you would expect the Lyman alpha coupling to be the dominant process. So it gradually monotonically increases, then X-ray heating takes over, you see a sign change, then the heated regions get interconnected with each other, and you see another sign change, and then it gradually decreases in amplitude because now X-ray heating is competing with the ionization process. The fluctuations in brightness temperature is being driven by these two competing processes. Now, yeah, I can explain it with a small toy model, but I'll go into that later if time permits. But if we compare it with the power spectrum, because that was my claim, right? You can distinguish between these models using bispectrum in a better fashion compared to the power spectrum. So it's not that power spectrum do not have the signatures of these processes. There are. You can see those kinks, ups and downs in the power spectrum, but they are rather subtle. And it is not necessarily easy to distinguish them that easily. The advantage of bispectrum is that it shows you the sign change. That's why it gives you a better handle to identify which IgM process dominates when. So I would then go into the effect of source model. So now in our simulations, this Grizzly simulation, essentially what you can play around with, you can play around with the X-ray heating efficiency or Lyman alpha coupling efficiency, etc., as well as the minimum halo mass that can host a source. So we played around a bit with the X-ray heating efficiency as well as the minimum halo mass, and we found that the features in bispectra does not change much. What changes is that they just get shifted in time. So you still see the similar kind of features, similar kind of sign changes or sequence of sign changes rather, which one can use to actually then recreate the cosmic dawn history in principle later on. So the source model, if you change the source parameters, the the bispectrum features more or less remain same. They will appear earlier or later depending on your source parameter models. That will actually help you in turn to constrain the source parameter models, etc. That is our claim, which we would like to basically verify later in a follow-up work. So just to conclude, the CDO at 21 centimeter signal is highly non-Gaussian. The bispectrum statistic can potentially capture this time evolving non-Gaussianity. The bispectrum, being potential probe of this non-Gaussianity, can probe the IgM physics, which is driving this non-Gaussianity. And bispectrum features can be used as a confirmative test because these sign changes you will not get from the power spectrum for the detection of 21 centimeter signal. So why do you see these sign changes? So the sign changes appear simply because of the fact when we look at the signal fluctuations, how we look at the signal fluctuations, So the background, for example, here, if we consider that purple region as my signal, then that red or that region works as kind of a background. So it's a purple on a red background. So in a similar fashion, your signal may be, the signal fluctuation may be coming due to the fact that you have a rather, let's say, negative background very early on when Lyman alpha coupling just started, and there are certain Lyman alpha coupled region distributed from each other, far apart from each other. So those Lyman alpha coupled regions are strongly negative, more negative compared to its background negative. So then it produces a sign that gives a specific sign to your fluctuation. Similarly, if your IgM is already heated, well saturated, and you have ionized regions in that heated IgM, that also contributes to a sign to your delta 21 centimeters. And as I have mentioned, that the power spectrum cannot capture this sign simply because it's kind of a variance. So you just deal with the amplitude. But bispectrum, because it's a product of 3 of these deltas, it kind of helps you to retain that large scale sign of the fluctuation. And that is what makes it more susceptible in terms of determining when what physical process is dominating. So with that, I would just conclude that the sign and shape of the bispectrum works as a kind of smoking gun for the dominant physical process in the IgM. So it is not only the sign, the sequence of signs that you get, that is what important. Okay, I will stop here.
Thank you, Suman, for your nice talk. So time for a few questions. So what is the motivation of considering squeezed limit?
Okay, the motivation of considering squeezed limit is to look for the large scale fluctuations in the signal.
And another thing is in one of your plot where you were showing all the processes. So why that plot not following the ionization plot? I mean, why the green plot not following the red plot in the low redshift regime?
Yeah. Nice question. So what is happening there? So if you recall, the red one started, if we go back here. So red one is this particular model, model A, where Lyman alpha coupling is there and photoionization is there. There is no heating. So now imagine you are creating ionized regions. So ionized regions gives you basically there is 0 signals coming from ionized regions. So the background right now is negative, and on top of you have a 0 signal region. If you take a Fourier transform, so let's say this ionized region is sphere. So that can be represented, if you take a Fourier transform, that can be represented as a window function. So if you create an ionized region in a heated background, where background is positive, and you have created a hole, a spherical hole in the IgM, then if you take the Fourier transform, the window function will come with a negative sign. Here the background is negative and you have created a hole. So there is one negative already times this negative. That makes it positive. That's why the bispectrum is positive, because there is no heating. The moment you inject heating, because now heating provides a kind of a positive background, mild positive background. On top of that, you are creating hollow spheres. That will give you a negative 21 centimeter fluctuation.
Thank you. One small last questions.
Can you go back to your slides where you show source modeling?
Yeah.
No, the plot.
Another plot.
The plot, source modeling plot.
Source
Very
modeling plot.
I think it's a third last.
Okay.
Third last.
Modeling.
Just third last.
Third last. Okay.
Last.
Okay.
Third last.
Sorry. This is where we discuss source model. Oh, okay. I remember. Sorry. Yeah.
So in the last panel, right panel, you not only just see the shift, but also see the change in the shape.
Yes.
So I'm not sure why this happens, because X-ray heating, I assume, is similar in models.
Right. So the change in the shape means this change you are talking about. This is going up again. Yeah. So if you follow this tail here, so if I go back one slide, so let us follow this. The green dash curve, that is the self-consistent model, that actually goes up like this, right? Yeah. Peak is different. I'm coming to the peak. So you are talking about the peak or the okay. Okay. So in the last one, right? So there I would this much discrepancy I would not put that much importance on that, because see there was just 3 points. We had just 3 points. It could be just because of the fact that we didn't have enough redshift snapshots at that particular this particular region. So I would not put that much emphasis on this particular sharp peak, because it depends on the redshift resolution of your simulation as well. We probably didn't have good enough resolution there. Yeah, no, thanks. That's a good question. Pratik has a question, and
So
there is one question from behind. Yeah.
sorry, my question is, I mean, what happens when you add noise? I mean, on top of these, do you still distinguish?
Yeah, so
different
that's
scenarios?
what we did actually in these two. Okay, we have not done that for Cosmic Dawn, but in these two papers, Mondol et al. And Tiwari et al., we have actually added noise and tried to, but those are particularly focused towards estimating UR parameters, where we didn't deal with Cosmic Dawn at all. So I do not have a straightforward answer to your question, but in case of UR, we figured out that at least in UR you don't see that many sign changes, because there is only one dominant physical process, that is ionization. There we could recover the feature, but I do not know about Cosmic Dawn yet.
I think we can. So we can.
There is one question at the back. If you can shout. Yes. Yeah. Okay. So how does that compare with the power spectrum? I don't have an answer to that question, but yeah, different K modes. For example, this is a different K mode, 0.5 MPC inverse. Certainly, the features will be different here, but yeah, we have not, more or less, we see that the similar features start to appear here as well. If you go to even larger K modes, where you would be probing the small scale fluctuations, they are also features are kind of same, but our motivation to choose the smallest K mode was to look at the large scale fluctuations mostly. Yeah, I have to check how does the power spectrum behaves in these K modes, and then probably I can say that.
Okay, thank you, Suman. Let's thank our next